Hello everyone, and welcome to this video presentation for our EACL 2024 contribution titled Multi-Relational Hyperbolic Word Embeddings from Natural Language Definitions. I am Marco Valentino from the IDEAP Research Institute, and this work has been done in collaboration with Danilo and Andre from IDEAP and from the University of Manchester. A natural language definition is a statement whose core function is to describe the essential meaning of a word or a concept. So by their own nature, natural language definitions are typically regarded as rich and reliable sources of information from which we can extract textual embeddings. A nice feature of natural language definitions, which represent the core of our work and contribution, is that they typically induce a rich semantic structure connecting defining and defined terms that can help us overcome or alleviate some of the limitations of existing textual embeddings, including lack of interpretability and controllability at inference time. To this end, we propose a multi-relational framework for deriving word embeddings exclusively from natural language definitions, which mainly consists in two phases. So we first build a specialized semantic role labeler for the annotation of natural language definitions from large corpora. And subsequently, we formalize the learning problem as a link prediction task via a translational objective. The idea behind the translational objective is that it can act as a proxy for minimizing the distance between words that are connected in the definitions, while at the same time preserving the semantic mapping that is required for an interpretable and controllable navigation and manipulation of the space. In order to implement our multi-relational framework, we rely on a well-defined set of semantic relations, which were defined in previous work by Silva et al., which typically describe the relationships between defined words in a dictionary and defining terms. These relationships tend to define the essential attributes of the concepts being defined, such as supertypes, differential qualities, and specific properties of different entities. In order to extract the multi-relational triples, we simply explore the fine-tuning of different BERT models applied for token classifications. In particular, we want to find a balance between efficiency and performance, and therefore explored lightweight models such as distribBERT for annotating large set of definitions extracted from external dictionaries. Thanks to the semantic annotation, it is possible to leverage the relational structure of natural language definitions for training. So in particular, in this work, we formalize the problem as a link prediction task by a translational objective function. The translational objective that we use is the one defined in equation 3. And as you can see, it can intrinsically minimize the distance between concepts and words, in this case, that are connected within a definition via explicit geometric transformations applied using the semantic relationships. So the idea is that we can jointly encode words and semantic relations into a latent space to then use the semantic relations at inference time to explicitly manipulate the latent space. In order to capture the global semantic structure of natural language definitions, we hypothesize that hyperbolic manifolds can play a crucial role. This is because recent work has shown that hyperbolic embeddings can represent a continuous version of trees, and therefore are more suitable for representing hierarchical structure when compared to Euclidean counterparts. To this end, we instantiate our framework in hyperbolic space by specializing the general objective function of our model. In particular, we follow recent work on multi-relational Poincare graph embeddings and hyperbolic neural networks to convert our general translation framework into an hyperbolic translation framework by casting each Euclidean transformation into the corresponding hyperbolic model. In order to assess the ability of our multi-relational framework in capturing the global semantic structure definitions, we train a range of word embedding models on a total of 400,000 definitions from WordNet, from which we are able to extract roughly 2 million triples. To compare Euclidean and hyperbolic spaces, we train two different versions of the model by specializing the objective function accordingly. Moreover, we experiment with different dimensions from both Euclidean and hyperbolic embeddings, training the models for a total of 300 iterations. If you want to know more technical details about the training, I invite you to check the paper directly. Moreover, we contrast our multi-relational approach against existing baselines and models that are specialized for extracting embeddings on natural language definitions. In particular, we contrast our models against distributional approaches such as word embeddings in the literature, like GLOBE and Word2Vec. We compare against autoencoders specialized on natural language definition and using LSTM-based models. And finally, we compare our approach against sentence transformers. This table shows the main results achieved by our model on word embeddings and similarity benchmarks. In particular, from the results, we can derive three main observations. First of all, the experiments reveal that the hyperbolic manifolds can yield a gain in terms of performances and can therefore better capture the global semantic structure of definitions. Secondly, a comparison with distributional approaches in previous work reveal the impact of the semantic correlations on the quality of the embeddings. And finally, we found that the multi-relational framework is competitive with state-of-the-art transformers, having the advantage of requiring less computational resources and also being intrinsically more interpretable with a lower number of dimensions. In addition, we perform a comparison with existing hyperbolic word embeddings in the literature. In particular, we compare our model against hyperbolic GLOBE and Word2Vec, finding that our approach can outperform both models. These results further demonstrate the impact of the multi-relational approach and the proposed definitional model on the quality of the representation. Finally, we design an additional experiment that tests the ability to encode out-vocabulary words via the explicit semantic relations encoded in the latent space. In particular, to perform this experiment, we first remove the test words from the training set and then approximate the embeddings of out-vocabulary words via geometric transformations applied to in-vocabulary words and semantic relations. For example, if we want to derive the word embedding for the word dog, then we simply average the object words appearing in the definition, such as carnivorous, as not, and then the corresponding semantic relations extracted via the definitional model. These allow us to approximate out-of-vocabulary words using the semantic relations via one-shot embeddings. The results in the table reveal the impact of the multi-relational approach when compared to a mean pooling baseline, and also remarks the superior capacity of the hyperbolic embeddings to capture the global semantic structure definitions. Our work still possesses a range of limitations, which we hope to address in future work. I invite you to check the paper for additional details. One of the main limitations we would like to avoid and overcome in future work is to move from static word embeddings to contextualized word embeddings, such as the one induced by transformers. In order to reproduce our results, I invite you to check our code, which is fully available online. And if you have any question, feel free to send me an email at marco.valentino@idiap.ch. So thank you for listening, and I hope to meet you at the conference and discuss our work in further details.